Hi there, everyone. Welcome to my talk. My name is Reuven Lerner, and this is my talk is called Generators, Coroutines, and Nanoservices. I'm really happy to be here. A few words about myself. So I have what I think is a super fun job. I teach Python. I go around the world. Well, in theory, I go around the world teaching Python at companies all over. Last year, before a pandemic, I was in the US and the UK and Europe and Israel, where I live, and India and China, teaching different corporate training courses about Python. I also have a whole bunch of online courses. I teach a set of courses called Weekly Python Exercise. I have a book, printed book, called Python Workout, which has someone in the chat just said that they've gotten it. So thank you very much. I appreciate it, which helps you to level up your Python with a whole bunch of exercises. And I have a free weekly newsletter called Better Developers, which is read by currently about 18 or 19,000 people each week. So the most important thing to start off with, this is not a talk about async IO. So from the title of the talk, which mentions coroutines, you might think that this has to do with async IO, because nowadays in Python, people, when they talk about coroutines, they mean async IO. This is not one of those. This is harkening back to an earlier period when we had coroutines that were working with generators. And on the one hand, you might think of it as something a little old, ancient, weird. At the same time, this talk is meant to both explain how these technologies work, how some keywords work in Python that you might not have understood before, and to start generating some ideas about how we might be able to use these technologies better. And at the end, I'll wrap up with a little bit of talk about async IO and how it fits into all of this. So let's start off with the dumbest function in the entire world, which is def myfunc, as you can see, return 1, return 2, return 3. So if I run this function and I print its return value, so now what's going to be printed out? Well, you're not going to be surprised to discover that it prints 1, right? That I told you it was the dumbest function in the world. Well, it makes sense, right? Because return means stop the function and return a value. And if you run this function through, say, pylint, it'll warn us that the final lines are unreachable. It will actually tell us, hey, you can't get to return 2 and return 3, which is, of course, true. And even Python's byte compiler ignores the final 2 lines. People often have this sense that Python is an interpreted language, but it's not. Actually, it's a compiled language. Before any Python code can be executed, it first needs to be turned into bytecodes. And when you write a function, when you define a function, that function is compiled into bytecodes, which are then executed. We can take a look at those bytecodes here if we use the dis module that comes with Python for disassembly. So if I run the dis.dis function on my func, what do I get? Well, it's going to load up the constant 1, and it's going to return that value. This is what return 1 is turned into. What about return 2? What about return 3? Gone, ignored. So even the Python compiler, which is sort of known for being kind of dumb, and for just taking whatever code we've written and turning into bytecodes, it's smart enough to realize we cannot get to return 2, we cannot get to return 3, so we're just going to ignore those altogether. All right, now that we've looked at a really dumb function, let's look at a slightly different function. What about this one? Def mygen, yield 1, yield 2, and yield 3. And I'm going to do the same thing as I did with my func before. I'm going to run it, and I'm going to print the result. So what happens when we run this code? Well, we actually get something totally different. We get this thing generator object mygen at blah, 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 all sorts of nonsense, which is not actually nonsense. It's actually the address in memory, which happens to be the same thing as the ID of the object. But we don't need to go there right now. What's going on? Why did we get this generator object back rather than just 1? Well, the difference is very simply yield. Yield is a keyword in Python. Yield is something that Python notices and does something with. And so when we define our function and Python is compiling it into bytecodes, it notices yield and says, wait, I'm going to do something totally different with this. This is not a regular function. This is a generator function. And so that means that when we run it, we are not going to be getting back a value right away, or at least not a value from the function body. Rather, we are going to get a generator object back. And we can see that. We're going to talk about what generator objects are in just a moment. But we can see this with dis.showCode. So this is also from the dis module, the disassembly module. But show code is a really great function that summarizes all the hints that Python leaves for itself in the function object. So we get a function name, the file is defined in, and all sorts of other things. And there are a whole bunch of flags. And those are actually binary flags that are set in, well, CO flags. And you can see here that it's marked as generator. So what happens when we define our function? Python notices the yield. Because there's a yield, it's tagged as a generator. And because it's a generator, when we run it, we get back that generator object. And by the way, if we try to disassemble it with this, as we did before to myfunc, it's a whole different kettle of fish. Now we're loading the constant 1 and yielding it. And then we're loading the constant 2 and yielding it. Then we're loading the constant 3, then yielding it. And then we are returning none. And returning none from a generator function actually raises a stop iteration exception. And we'll talk about that in a moment as well. Notice here, by the way, that yield is baked into Python. It's not just sort of a random keyword or something. It's not a variation on return. It's so baked into Python that it's one of the bytecodes that at the lowest level of the language, it really understands. So that's very nice that we're getting back to this generator, but what is a generator? Well, it implements Python's iterator protocol, and this protocol is deliberately really simple. Basically, you say to an object, who is your iterator, right? Which is the object that knows how to iterate for you? And in the case of a generator, it is its own iterator. We'll see this in a moment as well. Then you go to that object, you say, what is your next value? And use the next function for that. Give me your next one, your next one, your next one. And when you finally get to the end of the iterations, then that object should raise this exception, stop iteration. By the way, if you are of the opinion that exceptions are only errors, that is not true. And stop iteration is a perfect example of how Python uses exceptions for signaling, for indicating, hey, there's an unusual thing going on here, not necessarily for errors. So let's go over how a for loop works. Well, we have our for loop, right? Everyone who's ever programmed Python for even a day or two has done one of these. And so how does it work? Well, the for loop turns to ABCD, turns that object there and says, hey, is this object iterable? The answer is yes. So because the answer is yes, we go to the next stage. It says, okay, ask that object for its next thing, its next thing, its next thing. And each time we get the next thing, we assign that thing to one item. And then the body of the loop runs, we go back for more. Next thing, by the loop runs and runs for more. When the object wants to indicate that it's out of object, it raises stop iteration. No more elements, nothing more to return. And so in this case, we're going to get, of course, A, B, C, D, because we get A, then we get B, then we get C, then we get D. This, by the way, is why in Python, we don't have indexes. We don't care about indexes, right? Because we're just turning to the object and saying, give me the next one, the next one, the next one. Well, what about with our generator? What's happening here? Exactly the same thing. Notice I'm running my gen. So I'm saying, is it iterable? So the for loop is turning to the result of my gen to our generator object and saying, is it iterable? The answer is yes. So it says, okay, give me your next thing, your next thing, your next thing. And each time it will give us something new until it gets to the end, at which point it will raise stop iteration. Raise stop iteration, the for loop realizes at the end, and the loop, end of story. And we get 1, 2, 3, and then that's the end of it. And by the way, if I now say G equals my gen, if I assign that generator object to a variable, well, we'll see that I can get G and I can get iter of G. Iter of G is our manual way. You're probably never going to do this manually, but you can turn to an object and say, hey, who is your iterator? And you'll see that the two IDs, the two addresses in memory that we get back here are actually identical, which means that the generator is its own iterator. So when you say to a generator object, hey, who's your iterator? It says, oh, I'm my own iterator. Well, what about next? Well, if here's my generator on the right, just to sort of keep track of it. So when I say next G, what next does is it runs up to and including the next yield statement. So next to G says run through the next yield statement. It says yield 1, and then it goes to sleep. Basically, the function is still around, or the function, the stack frame of the function is still around. The function doesn't return, the function doesn't exit. It sticks around, and it knows where it went to sleep. So then when we say next G, it picks up from where it left off, and then runs through the next yield and returns. And then picks up from where it left off, runs to yield, and then finally at the end, we get stop iteration indicating we are at the end. Very important to understand that next is always going to say run through the next yield statement. And this can be a ton of code, or this can be a tiny amount of code. And you can have it in a loop, so that with each loop iteration, you are then yielding and yielding and yielding. Each time we hit yield, we get a value back, and the function goes to sleep until we restart it. What's really nice is that we're dealing with a function that works just like all other Python functions. And so the function state, meaning its local variables, remain across each of these calls. So you can set something up at the start of your generator and keep referring to it. And that's going to be key to what we're going to see in a little bit. So here's like the classic example of a generator in Python. This is the Fibonacci sequence. So we're going to start off with our generator by defining first and second, two local variables, 0 and 1. And then we're going to say while true. Notice, this is going to give us an infinitely long series. But we can express this infinitely long series as a generator because we know that we're going to be getting the values one at a time. We don't have to worry about filling all of our memory with infinite amounts of data. So what happens in the loop? We're going to yield first. We're going to get 0. And then we're going to do a little switcheroo. We're going to say, well, take second and make it first. Take first plus second and make it second, meaning move everything to the left. And each new value will be the sum of the previous two values. So if I say g equals fib, and again, I'm going to do this manually, but we're going to be doing a lot of things manually in this talk. Then I say next to g, I get 0. Next to g, I get 1. Next to g, I get 1, and on and on. Here's what you never want to do. List of fib, because what's going to happen? List says, oh, I'm going to create a list from all the things that it returns from iterating over fib. So it says, give me your next, give me your next, give me your next, and it will never raise stop iteration. It'll just use up all the memory in your computer. So maybe don't do this on your own computer, but if you have a colleague or a friend or someone you don't care if they're not your friend anymore, perfect place to experiment. What about another example? So here's something I like to play with called read n. Normally, if I iterate over a file, I'm going to get the elements or the lines one at a time. Each time I iterate over the file, I'm going to get the next line and the next line, the next line, up to and including the next new line. Here, though, I'm saying, well, maybe I don't want to get one line at a time. Maybe I want to get n lines at a time. Maybe I'm dealing with a file that is configured in a certain way that would be really nice to get chunks of like 3 lines or something at a time. So what am I going to do here? I'm going to define my generator such that I open the file, and then once again, I'm going to do while true. But now, what am I going to do with each iteration? I'm going to read n lines. I'm going to run f.readLine, which always returns a string. If I'm at the end of the file, it returns an empty string. I'm going to run it n times. So I'm going to get n strings. I'm going to join them together. And I'm going to say, hey, if output, meaning if my string is not empty, then I'll yield it. But if it is empty, if the output is empty, then I'm going to break. What happens when I break out of the loop? The function ends. What happens when the function ends? It raises stop iteration. We have exited. So this actually works really well, and it all depends on yield returning a new value with each iteration. Next example, next vowel. So what I can do is I can run this I can define get vowels that'll run on a file name. I'm going to open the file, and I'm going to read through each line because that's how we iterate through files. And then I'm going to iterate over each character in the line one at a time because one line is a string. And then I can say if the current character, lowercase, is A-I-O-U, a vowel, then yield it. What happens if it's not? Then we go to the next one, next character. What happens if we're out of characters on this line? Then we go to the next line. What happens if we're out of line? Stop iteration. And this is all, once again, because yield will yield one thing. And if we don't yield, then it'll keep running until it hits the next yield. So when should we use generators? So if we have a potentially large or infinite set of values to return, right? We don't want to use up tons of memory with all of our data. Rather, we can sort of get it one chunk at a time. Often generators are used because it's easier to express an idea as a function. And also, maybe we have to set things up like a network connection or open a file, and then we want to just keep that state going in our generator, and it'll stay across our different iterations. Okay, well, what about this? This is where things start to get a little weird and wacky, but also interesting. Def my gen, x equals none, while true, x equals yield x. Well, that's kind of weird, right? Because before we were saying yield is a statement. It returns something to us that will go back. But now yield is an expression. It's something that has a value that is returned to us. What the heck is going on? So when we use yield as an expression, meaning on the right side of assignment, doesn't have to be there, but it's typically going to be there, all the rules for generators still apply. Each call to next runs through the next yield, as before. After yield, it goes to sleep. But now yield can be used for two-way communication. Now we can inject a value into our function. By every time it yields to us, it then waits to get something from us. We can send it a message. And that received value replaces yield in the expression and then is assigned to whatever was on the left-hand side. Yeah, but how are we going to send a message into our generator? Well, we're going to use the send method, of course, right? We can advance our generator next. But we can send a value if we use the send method. And notice that's a method rather than a function. And that is an inconsistency, I agree. You can also say just g.send of none, and then you're always using the method. So what you can do is you can say def my gen, x equals none, while true, x equals yield x, x times equals 5, just like we had before, okay? So I'm going to say g equals my gen. I'm going to create a generator object. And now I'm going to say next of G, I need to do what's known as priming. What's priming? Priming is running through the first yield statement on the right there, so we get a value back. And that's always going to be, well, whatever it wants to return. Here it's going to be none. But now we've gone to sleep on the right side of that assignment. So whatever we send will be assigned to X. And sure enough, if I say G.send of 10, that means that now we've got X equals 10. X times equals 5. 5 times 10 is 50. We go back to the top of the while loop. We yield X, so we get 50 back. And now it's waiting again. So I say G.send of 23. X equals 23. X times equals 5. Now it's 115. Go back to the top of the loop, yield it, and we get that back. I can even say G.send of ABC or G.send of 123. I can send any Python object I want. And so long as it works within the context of this API, I'm doing great. This is what's known as a coroutine. And a coroutine is a generator that waits to get input from somewhere else. The data is received within the yield expression, usually on the right side of assignment, and our local state, as before, remains across calls. Now, you might remember, or you might know, that when Python 3.8 came out, it introduced what was called the walrus operator, right? No one calls it the assignment expression. Everyone calls it the walrus, and you're not sure why it's called the walrus. Tilt your head about 90 degrees to the left, and you'll see it has eyes and tusks. And okay, fine. This expression, assignment expression operator, the walrus, is one of the most controversial things I've ever seen in the Python world. It led to a whole lot of crazy discussion and anger and so forth in the Python world. What does it mean? It means that we're going to be able to assign, and assignment then becomes an expression. We get the value back. So what are we going to do here? We're going to say def of mygen, X equals none, just like before. But now we can tighten up that while loop. I no longer need to have while true and then assign and then check. Rather, I can just say while X walrus yield X. What this means is if I get a value that's none or anything else that's empty from the yield sent to me, then that will be assigned to X and be an expression, and we will exit from the loop. That means exit from the loop whenever we get none or something that's empty. But if we don't exit from the loop, then we get the value. Notice also we need to say yield X in parentheses. And the reason we need to do that is just for syntactic reasons. Otherwise, Python gets really confused. So I now have rewritten my coroutine such that it uses the walrus operator and is thus a little shorter and a little cooler. I think we'll all agree. What if you don't want to prime your coroutine? So David Beasley had a whole talk back in 2009 about coroutines, about generators, and he suggested using a decorator, which he called coroutine. So you would put @coroutine above your generator function, and it would automatically run next and then return the primed coroutine. So I'm not going to do that here, but that's actually not a bad idea because it's just a pain to do the whole priming thing. So what? So what? Like, I've now shown you a whole bunch of things, and you might be saying, okay, and where do I use coroutines? And I often say that coroutines have looked like a solution looking for a problem, right? It's like, oh, we came up with this fantastic technology. Where do we use it? I don't know. I'm sure someone needs this for something. And so I've been struggling with this for years. And I've been trying to figure out where to use coroutines, how they fit into the Python ecosystem, because there was a lot of effort put into them to add this sort of functionality into Python. And yet, no one seems to really use it very much. Moreover, as we'll see in a bit, some new keywords were added to the language a number of years ago, and no one quite knows how to use those either. So what I want to do is give you some ideas for where this can be used, and we'll see where it goes. So my big idea is coroutines can be sort of like nanoservices, right? Some of us were joking in the chat before I started about like how big are nanoservices. So where does this term come from? And I've made it up, I think, right? So if you really hate it, I did not make it up. In any event, many applications, like service applications, have what's known as a microservice architecture. So rather than having one big program that handles everything, you have a caching server, and you have an authentication server, and you have a database server, and you split things up into many, many, many different servers. All right, and so you access each microservice via a different API. So I think of coroutines as nanoservices, meaning they are super, super tiny in-memory services. We don't have to worry about network overhead or object overhead or thread overhead or process overhead. We're not switching threads. There's no context switch. And it keeps its state across different iterations. And so You'll need to create your own protocol for a coroutine, but you could use Python's very rich data structures. And this means then that basically, right, we can create these little services and we can use them from within our program. What do I mean? Well, here's a few examples. So one example is MD5. So MD5 is a popular hash function. It's in hashlib, but I don't know about you. I found it a bit of a pain to use in Python. So what I'm going to do is I'm going to create a little MD5 service within my program. Okay, so how's that going to work? Well, I'm going to say here, import hashlib. That's where it lies, that's where it resides in the standard library. Def MD5 gen. I'm going to say output equals none. And then I'm going to use the walrus, right? While s colon equals yield output. So we're going to get a string from someone. We're then going to create a new MD5 object, m equals hashlib.md5. I then have to turn the string into bytes. That's one of the annoying things about dealing with this. So I'm going to say m.update s.encode. So I'm going to say s.encode, turn into a byte string, hand that to m.update, and then we're going to say, hey, MD5 object, what's the hex digest? What are the 40 hex bytes I can get back in that output? And it works, right? G equals MD5 gen, g.send none. Why am I doing that? Got to prime it. Then I say print g.send of hello, and we get something back. Just saying goodbye, we get something back. I kept out the MD5 signature. I don't think it's that exciting. And then I can say g.send of none. What happens when I get none? Well, the loop exits because of the walrus operator there. And then the generator function exits, which means we get a stop iteration. So we exit from there. Here's another example. So let's say I want to get the weather forecast for a particular city. So it turns out that the World Meteorological Institute, which is affiliated with the United Nations, actually has a server where if you know the number of your city, and they actually have a chart of that on their website, you can pass it a URL and they'll give you back JSON. And so what you can do is you can request the weather for a city, any number here, .json. I'm going to use request. So request is a nice .json method there. And then you have to dig into the forecast. But I can say, give me one forecast per day. So I say G equals get forecast 44. And then each time I say print next of G, what am I going to get? I'm going to get the next weather, the next weather, the next weather. That's pretty great because it means I'm only requesting it once. I'm only going out to the network once, but I'm getting multiple values back. And you might be saying, wait a second, that's not a coroutine. like after all this talk about coroutines, I was supposed to generate a coroutine. Okay, so let's do something slightly different here. Let's say get forecast. And while city ID equals, so I'm going to get a city ID, and then I'm going to yield each of the forecasts for that city. So I'm going to say G equals get forecast, next of G. And look, now I'm going to get send a city number or none. This is like my super primitive protocol. So if I say G.send to 44, we'll get that. And I can send whatever I want now until it runs out. Send 44, send 44. So I'm going to get a few different weather forecasts. And then if I say send 44 another time, we get it. And then it says, oh, I'm back to the top. Basically, we ran out of weather forecast, so it goes back to the top of the while loop. And now I can send a different city again and again and again. So basically what I'm doing here is I'm caching the weather information. It's in memory, so I'm not saving memory, but I'm not having to deal with this huge data structure. It's broken down for me. Here's another example as food for thought. I can use PsychoPG2, which is a popular library for connecting to PostgreSQL. So I can connect to the database with a database string, and I can say, well, I want to select all the people, all the people with whatever first name, last name, birth date they have. And I populated the database with 4 people, me and my 3 children. So this is going to be a very small database. And I can then even do a little trick here where I can get information. I'm going to get a dictionary, right? You can see here my while loop. What am I getting from yield? I'm getting a dictionary. So what we can do is make the dictionary keys match up with the fields in the database. I can create my own tiny little query language here. And sure enough, that I can print the query. And then I'm going to just do for one record and curl up fetch all. So I'm going to get all the records that matched, yield one record. How does this work? How does this look? Well, I can say G equals people API. So I'm going to create my generator. I'm going to prime it, next G, send a query or none to quit. And so now I'm going to send a query. I'm going to say G.send of, here's my dictionary, last name Lerner. And sure enough, it'll bring me back one value. And that says, and then I have to say G send whatever, because like I have to get it back to where we were, send a query or none to quit. I'm going to say now G.send, last name is Lerner Friedman. That's my children's last name. And so there we get 1, 2, 3 elements, and then it's back to the top. So basically, we've got this little API going. Now, I'm not trying to tell you that you should reinvent the wheel and create your own database query system, but it shows you the possibilities for what you can create and how you can create rich data. The thing is, how can I tell the generator that I'm really done? Right? What if I want to exit? I don't want it to raise a stop iteration. I can actually use the close method. And the close method says, I'm done. You don't have to continue sticking around, right? Don't just go to sleep but keep the stack frame active. Rather, go to sleep and exit, and that's it. But what if I want to do something a little different from that? Not close the current generator, but rather I want to send it a signal of some sort, not send it a message that we know we can do with send. But I want to kick it out of the inner loop and get it back out to the outer loop. Well, for that, it actually turns out that we have an option, and that is the throw method. So what happens is we can run the throw method on a generator, and that will raise an exception of our choice inside of the generator. It's like we're really throwing an exception. We're causing the exception to happen inside the generator there. So how can we do this? So for example, I can say here, class of different city exception. And I want to point out that using a custom exception is really a good idea. You don't want to use just any old exception, and certainly not a built-in one. And now I've rewritten my code a little bit. So I'm going to get the city ID fine. I'm going to get the request, and I'm going to say try. Right? As I tell my kids, it's always good to try. Right? And so we're going to try to retrieve it. And we do try and yield. The thing is, though, every time we do a yield, what happens? That's right. The generator returns a value and goes to sleep right there. And if we then say throw, that's where the exception is going to be caught. And we can say, except for a different city exception, continue. What's going to continue? The while loop, meaning go back up to the top. Let me show you how that works. So I'm going to say G equals get forecast. Next G, got to prime it. Send 44, got it. Send 44, got it. Throw a different city exception, and now it goes back up to the top of the while loop, and it once again asks us for a city, and now we can get a different city. So our nano service here is available via a very simple request and response interface. It uses data structures for input and output. We can keep state across the invocations here, which is perfect for network connections, database connections, and we even saw that it's able to yield one element at a time, which is pretty great. All right, let's do a little thought experiment. Let's say we want to put lots and lots and lots of functionality into our same coroutine. I know this is a bad idea, and I know this goes against everything I've told you so far. So let's say we want to have inside of the same nano service, mega service, MD5 hashing and weather forecasting. Right? There's an old fake advertisement in the United States from a comedy show where they talked about it's a floor polish. No, it's a dessert topping. It can be both. So I feel like this is almost as bad, but less tasty. So what am I going to do here? I'm going to have this huge honking combined generator, and it's going to do what we had in our previous two generators. It's going to say while s equals yield, send 1 for weather, 2 for MD5, or none to exit. So if the person sends 1, then we're going to start doing our weather forecasting. If they send 2, then we're going to do our MD5 hashing. Oh, wait, does this work? Actually, it does work. It's a terrible idea, but it works. Right? As I like to say, unfortunately, it works. So we say here, G equals our combined generator. We're going to do next. It sends us the message. Send 1. Oh, well, now it wants a city number. So I'll send 44. Great. Then I can throw an exception. I'm back at the top. I can give it a number. Or I can throw the exception. I can send none. And I'm back at the way, way tippy top. I can say I want to do MD5 hashing. Here's the hash for hello. Here's the hash for hello, exclamation point. Fantastic. And once again, unfortunately, this works. How can we improve this? And let's think about this. A generator function is basically a function, right? How would we do this if this were a regular function? Well, if it were a regular function, we'd break it down to the smaller parts, right? We would take our function, break it apart, and then have little functions. Let's do that with our generator. So I'm going to now say combined generator is going to be a very top-level, high-level function. It's going to say, if we got 1, then I'll run the city generator. And if I got 2, then I'll do the MD5 generator. And then I separated out the 2 generators there. The only problem is this does not work. Other than that, it's great. Because I say G equals combined generator. Next, we get that. I'm going to send something. It ignores it, completely ignores it. Why is it ignoring it? Let's look at this. Right? I showed you here. If s equal 1, city generator. What happens when you call a generator? You just get the generator object. So we're not actually incrementing the generator. We're not running next on it. We're just we're not even returning it. So what can we do? It's not enough. We're going to need to yield something. Now, maybe we can just iterate over the items that generator returns, but that's not going to be enough. Because you have to imagine how we have 3 things. We have the outside person who's sending the message. We have our combined generator in the middle, sort of acting like an agent. And then we have the actual MD5 generator or the weather forecasting generator. So what happens from the outside if I run next or send? It somehow has to get past this into the end one, right? It has to sort of do a pass-through. let alone what about throw or close? This is where yield from comes to the rescue. Combine generator can be rewritten to say if s equals 1, yield from city generator and yield from MD5 generator. I cannot tell you how many people are thoroughly convinced that yield from, which was a new keyword introduced into Python, I believe 3.3, would they really create a new keyword just to have us do a for loop? That's what a lot of people think it is. They're like, oh, if you want to iterate over a subgenerator, then just instead of doing a for loop, use yield from. That is not wrong, but it doesn't even come close to describing what's going on. What yield from does is it provides bidirectional communication between the sender on the outside through the agent in the middle all the way to the inner one. So the inner subgenerator and the outer caller are suddenly talking to each other. They can throw, they can close, and they can send. And it works really well. Yield from is designed for sub-coroutines, if you were. And so now what I can do is say G equals a combined generator next of G, and then we can do send of 2 and send of hello. Whoops. And like we can go through each of these pieces and it works the way we would want. So let me talk about async IO for a moment. It is absolutely positively true that early versions of async IO use generator functions. Now, what is async IO? Async IO basically says enough of this context switching craziness, either to different processes or to different threads. There's too much overhead there. Let's have one process, one thread, and each task we want to run will be on a loop. And we'll just go through each of the tasks on the loop. Move a little, move a little, move a little, move a little, move a little. What do I mean by move a little? Meaning execute a little bit until you can stop, right? Everyone gets a little time slice of the clock. Now, you could argue that's exactly what our operating system is doing, but it's not. Our operating system is stopping things at a certain point. It's using what's known as preemptive multitasking. What I just described is something that used to run on many computers, something known as cooperative multitasking, where all the tasks need to behave well. So if you have an async def, if you have an async IO function running the way I just described, it can, in theory, run forever. It doesn't ever need to await. So early versions of async IO use generators because they fit the bill. They allow you to run them for a little bit using send or next. They will stop and go to sleep, and then you can go on to the next function. But a number of years ago, Python decided to get away from using explicit generator functions and started going in the direction of using keywords. Now use async def to say that you want to create a special definition, a special function that will create tasks for async IO. And await, which basically says, I know that something's going to take a long time, so I will give up control of the CPU. Just come back to me if you don't mind. So the ideas are similar. There is some overlap. And historically, there was especially overlap. And you'll find lots of documentation online that makes it sound like the two coroutines are the same, but they're not. Don't be confused too much. So after all this, should you use coroutines in the way that I've been describing? So I think the answer is yes, but, right? They can be very useful. They really provide you with a speedy, in-memory, arbitrary API using rich data. You can get lots of data one chunk at a time. It knows how to divide into smaller pieces. It can use yield from, so you can have all these sub-coroutines and sub-generators. But there are problems, right? These are not well understood. And it might seem weird to be using send, so you'll want to probably put some sort of API around it, some sort of layer around it. And when things go wrong, it can be hard to debug. David Beasley, in his talk, mentioned, I think he made an analogous to like high-powered TNT, right, or some other explosive. We're very, very useful in the right place at the right time, but it can blow up in your face and cause trouble. So if there are questions or comments, I would be delighted to address them. Please feel free to contact me. I'm on Twitter, I'm on YouTube, and of course my Better Developers list as well. Okay, I'm going to unshare my screen now, and I'll be delighted to answer questions and comments. All right, well, I'll hang out here for a bit longer if people have questions or comments. And I very much appreciate everyone coming to my talk. I am super, super excited to have been here for some value here for PyCon Africa. And I really and honestly was hoping to actually come physically to PyCon Africa this year. So we'll have to hold it off for next year or 2 years from now, whenever it's possible. Thank you so much, folks. Thanks, Joseph. Okay. So Joseph says, I didn't quite get the difference between coroutines and async IO. So let me describe it this way. So here's the thing. So what we did here, I'm just going to move my window over to where my camera is, so I'm not like looking over to the side. And there we go. So historically, like back, I don't know, 10 years ago, 15 years ago, they started the coroutines as I described them here. We had generators, we had coroutines, and so forth. Those ideas then led to the development of async IO. So there was a point in Python history when if you wanted to create a coroutine, as I showed you here, you could. And with a little bit of tweaking, not even very much, it would work in async IO as well, right? It was basically the same thing. And there were even decorators that you would use to turn a generator into an async IO coroutine. At a certain point, for reasons that are not quite obvious to me, I'm guessing have to do with performance. They said, you know what, we're going to stop this. We're going to have async IO have its own async IO defs. So they're not compatible anymore. I was just reading up on this earlier just to double check. But you can no longer use async coroutines are now defined with async def. They're not iterable, so you can't run them in a for loop. You might be able to use Python generators or like the coroutines that I showed today in async IO, but I don't believe so. I believe they've now diverged. So I find it useful to teach people about actually these sorts of generators and coroutines before talking about async IO because the ideas are similar and overlapping, but they're not compatible with each other. That in our nano routine, nano service coroutines I showed today, you're really depending on some service, right? Is going to say send, send, send. Whereas in the case of async IO coroutines, it's the event loop that every n seconds or n microseconds, whatever it's going to be, is going to basically do a send. But it's also not sending any data. It's just running it. I guess that's actually a good difference between them. That you need to, well, I guess it's a way to, like the data sending is happening in the await. The data sending is not happening with the loop sending it. I hope that makes it a little clearer. And Nikhil asks, in one of the first examples, you primed the generator with send none, which was in the walrus operating while. Oh, why did the loop not stop then? Fantastic, fantastic question. Okay, right. You would think that if I say send none, and I've got the walrus operator there, that it's immediately going to exit, except that was it was the first time. So the first time, like if I have a brand new, spanking new baby generator coroutine, and I send none to it, that's just going to run through the first yield. That first yield is on the right side of the assignment, not on the left side. So the right side is returned to us, and then it's waiting for us. Then we send. The second thing we send is then going to go into the assignment and go into the while. So that first thing is actually never seen by the while. And is await syntactic sugar for yield from? I have not checked. I don't believe it's syntactic sugar, but I think it's super close. I don't think await uses yield from, but I think, like, again, there are overlapping things here. That await basically says, I am going to wait until I get data from such and such, which is similar in some ways to yield, right? Yield from is for that pass-through. I don't believe that await does any sort of pass-through stuff, but I could be wrong. But like await and yield, they have this whole new idea in Python with async called awaitable. And awaitable things are not generators per se. They have to actually have if I remember correctly, a dunder await method defined on them. So again, like there's overlap, but they're not the same. And I am myself trying to sort of sort out how to describe exactly how they are different from one another. I should add, by the way, that earlier today, when I was trying to like just double check and read up on some things, so of course, one of my search results ended up being Stack Overflow. And I said, oh, I see someone's talking about async and someone's talking about generators. And then I realized they were talking about JavaScript. So I really have been out of the JavaScript loop, so to speak, for many years. JavaScript event loop, I guess you could say. But I knew that JavaScript had obviously Node.js. And I knew that JavaScript had generators. I did not realize that they had gone through anything similar to this in the Python world. So so it could very well be that there's a similar sort of overlap there. I'm actually curious to learn more about this now. Any other questions that people might have? Personal problems you want to share? And all right. Well, I guess there are no more questions. So if you do have questions after this, or you think of them, or you just don't want to share them in public, I'd love to hear from everyone here. Thank you so much for attending my talk, and I hope that you stay safe, enjoy the rest of the conference, and hope to be in touch. And as I said, even meet you in person at some PyCon Africa in the near future. Thanks, everyone. I really appreciate it.